Okay, good morning, everyone. So let's continue the discussion last time where we talk about, we finished the entire discussion on combinatorics. Yeah, and basically we figure out multiple scenarios to calculate different types of combinations. So in the homework problem, homework 3, those problems are, some of them are very tricky. So you can try to connect the problem statement to one of the problems that we have discussed in the class. And today we are going to talk about repeated Bernoulli trials. So we have discussed this before, but at that time we haven't introduced those combinatorics. So let's visit this Bernoulli trial again. So repeated Bernoulli trials, like you can think of repeatedly flipping a coin. Well, each time in each trial, you have probability P, small p, to observe the event E, and probability of Q, which is 1 minus P, to observe its complement. This could be a head, and the complement could be a tail in the case of flipping a coin. Or this could be a probability of success, and this is the probability of failure if you take repeated exams. So each Bernoulli trial is parameterized by this parameter P. Once we know the success rate, we know the failure rate. It's 1 minus P. And we denote 1 minus P as Q sometimes for convenience. Then we can look at this distribution Pnk, and this notation means the probability that the event E occurs k times in an independent trials. But you flip a coin for repeatedly for n times, and you look at this event, well, you observe k heads over these n trials, exactly k heads. Okay. And then we are looking at the probability of such an event. Okay, so this could be done by leveraging the combinatorics that we just discussed. So we have n independent trials. So I'll put here n positions. Okay. And in each trial, we could have E or E complement. Okay. That is for every single Bernoulli trial. And we are looking at the event, well, among these n positions, we have exactly KEs. Okay, we have exactly KEs. And then we have, because we have KEs, so the rest of the locations must be filled with E complement. So these are E complements. And because we are looking at we only care about the occurrence, the number of occurrence of E. Okay, we don't care about the positioning or the ordering of this occurrence of this event E. So this is like one of the combinatoric problems that we have discussed. So basically, among these n positions, we only want to choose k, a subset of k objects out of n objects. So it's choosing k from n. Okay, and we don't care about the ordering. So we have this many number of different choices. And then for each scenario, for each choice, the E happens k times and E complement happens n minus k times. So we can calculate these probabilities independently because we know they are independent trials. So by the independence of probability, the probability of this joint event is equivalent to, so the probability of E occurs k times and E complement occurs n minus k times. So this is given by every time E happens with probability P, and it happens k times, and the other complement occurs with probability 1 minus P, and it happens n minus k times. So this is the probability of this entire event. So this is probability that E occurs k times, exactly k times in n independent trials. So we call this the binomial distribution. It's a very famous distribution. Later on, we will introduce many other types of distributions. So this distribution characterizes the such a type of event. Where you have n independent trials, and k of them will succeed. Then the probability of observing such an event follows such a distribution. And we can see that this distribution is parameterized by two parameters. We just need to know the total number of trials and the success rate for each independent trial, individual trial. Once we know n and p, you can see once we know n and p, then this distribution is well defined over k. Okay? Depending on how many occurrences are you interested in, we can calculate this distribution characterizes the probability of such an occurrence. So here we leverage the combinatorics that we discussed last time. And then a very closely related tool is the Bernoulli's theorem. And the statement of theorem is this. So again, we have n independent, we're looking at n independent Bernoulli trials. And again, we assume that for each trial, the probability of, for example, success is with probability P. And so the complement is with probability 1 minus P. So the setting is the same as, exactly the same as the one that we discussed about. So for this independent repeated Bernoulli trials, we denote K as the number of occurrence of E. Right? So basically, you run these independent Bernoulli trials, and then you count how many times does the event E occur. Okay. And this case is random, right? Because according to the Bernoulli probability rule, it may happen that this E never occurs over these independent trials, right? Or it may happen, it may occur once, twice, 3 times, up to n times. So the range, so K is random. And it belongs to the range 0, 1, 2, up to n. So this capital K is different from the small k that we talk about here. Here's the small k is a given integer. We are looking at the event that E occurs exactly small k times. So this small k is a given integer in the distribution. It's a parameter. But this capital K is that, okay, you run this independent Bernoulli trials, and we are interested in the number of occurrence of this event E, which is a random thing. Well, the first question is, how big is K? Intuitively, okay, let's follow our intuition and try to get an estimate of this capital K. We have n independent trials, so every trial we can treat them independently. And in every trial, E occurs with probability small p. So basically, in every trial, we have probability p to observe the event E. Right? There's a probability p for observing E in the first trial. And this is kind of the expected number of occurrence of E in the first trial, right? Is the probability of occurrence multiplied by 1. So this is the expected number of occurrence for the first trial. And then we have n trials. So we are going to adding up all the expected occurrences over n trials. So this gives us n times p, which is the expected value of K, right? And intuitively, this makes sense because you did in total n different trials, n number of trials. Each trial you succeed with probability p. So the total number of the expected number of success is roughly given by the number of trials multiplied by the success rate. So we expect that K is roughly, although K could be a random integer, take values among 0 and 0, 1, 2 up to n. In practice, when we perform a large number of trials, we expect the value of K to be somewhere around now this expectation. And indeed, Bernoulli's theorem gives us a quantitative way to evaluate this, to evaluate the deviation of K from this expectation. So the Bernoulli theorem says that, okay, let's denote K divided by N as the empirical estimate of this probability small p. You can think of like you perform an independent Bernoulli trials, and suppose you observe capital K number of occurrence of E. Then by calculating K over N, this is kind of the empirical estimation of how likely that event E may occur in each trial, right? You succeed K times out of N times. So this is like the empirical estimate of the success rate. So this is like an empirical estimate, P hat, let's say. And this empirical estimate is random, right? Because in practice, whenever you try this Bernoulli, repeated Bernoulli trials, every time you may get a different number, capital K. So this entire estimator is a random estimator. And we care about the deviation, the difference between this estimation and the underlying true value P. Okay? Because in this experiment, we are given that in every trial, E occurs with probability P. So this is the estimation, this is the underlying truth. And we care about their difference. In particular, we care about their absolute difference. And Bernoulli's theorem says that the probability that such a deviation is bigger than epsilon. Epsilon is any given accuracy that you want to have. So the probability that that such an estimator deviates from the true value by epsilon is less than this number. Okay, so the probability is less than this number.
What's epsilon against?
Sorry?
What's the epsilon?
So epsilon is any number that you can, positive number that you can specify. For example, so this is a rough estimate of the probability of such an event, and this event characterizes the deviation of the empirical estimator from the underlying true value. Okay. And we can use this theorem to roughly estimate how many, for example, okay, let's consider how to use this theorem to draw some useful conclusions. For example, I want to make sure the probability with high probability my estimator deviates from the underlying truth. Okay, if I want to make sure with 99, I should put a small number here. Okay. For example, I specify epsilon to be 0.001 and I specify the probability to be 0.01. So this means that I want to make sure with a very small probability, okay, with less than 1% of probability, that the estimator, this empirical estimator, deviates from the underlying truth more than 0.001, which means with 99% of probability, this difference will be smaller than 0.001, right? So this implies now the complement event, think about this, the complement event the complementary event is less than or equal to like 0.001. This is complementary to this event. This complementary event by complementary property of probability law is 1 minus the probability of the original event. Okay. But we are given that this probability is less than 0.001. So this is because there's a negative sign. So this is bigger than 1 minus 0.01, which is 0.99. So if we have this, then we can conclude that with more than 99% of the chance, these two will stay within a small, will have a very small difference. So the estimator is very, very close to the underlying true value, true probability. Now the question is that in order to get this, how many number of independent trials should we have? We just use the Bernoulli's theorem. We are given that epsilon is 0.001, and we are given that P1 minus P over N epsilon squared to be 0.01. Right? So you can plug in epsilon into here and solve for the number of trials, and you will find that the number of trials depends on your target accuracy, depends on the probability. This is the confidence level. Depends on the confidence level that you want, and also depends on the success rate of your underlying Bernoulli trial. Okay, given these parameters, you can estimate the number of trials you will need in order to guarantee that with more than 99% of the chance, your empirical estimator will be close to your true probability within a small range. Okay. So this is a very, very useful estimation of Bernoulli trials in practice. Now we call this the weak law of large numbers. So roughly speaking, you can see that if n goes to infinity, then this probability will decrease. If I fix all the others things, okay, I fix epsilon, fix p, and let n goes to infinity, meaning that I am performing infinite number of independent trials. Then this, on the infinite number of trials, the empirical estimator will be very, very close to the underlying true probability, in the sense that the probability that the deviation between the two is bigger than any epsilon will goes to 0. Right? So you have a 0 probability to deviate more than epsilon, and this epsilon can be arbitrarily small. So later on, when we talk about convergence of random variables, we will know this is a convergence in probability. So this is how we utilize this Bernoulli theorem. You have to specify, you specify some parameters and you can estimate the other parameters. Or on the other hand, let's say if you can at most perform 100 Bernoulli trials, okay? So if this n is given, you cannot change n, then you can roughly estimate for any arbitrary epsilon, you can roughly estimate the probability of this deviation. Okay, so this Bernoulli theorem directly gives you characterizes the probability of deviation is bigger than a threshold epsilon. And another very useful tool is called Borel and Cantelli-Lama. This is sometimes very useful when we characterize the occurrence, the number of occurrence of events in the infinite limit. Okay. So let's consider a sequence of events. Okay, we have sequence of events. Now consider the following two events. One is B, event B that event B means that among this sequence of events, infinitely many of them will occur. Okay, so this, but for each event, for example, E1, it may occur or may not occur, depending on its probability. For E2, it may or may not occur. Now we consider the event that among these events, infinitely many of them will occur. Okay. And its complement is finitely many of them. Okay. Right. These are very two extreme events. Well, you have a sequence of observations and you care about whether or not this a certain thing may occur infinite times. And the Borel-Cantelli-Lama, we call it BC-Lama, says that we have two parts. The first part says that, okay, if I know the probability, if I sum up the probability of all these events, I sum up the probability of all these events. If their summation is convergent, meaning that if the summation, okay, from 1 to infinity is less than infinity, then PB equals to 0, right? And PB complement equals to 1. Which means that in this case, with probability 1, only finitely many of these events will occur. Okay. And with probability 0, infinitely many of them will occur. So basically, with probability 1, you can only observe finite many of these events. And this condition has no requirements on the events. They may be dependent, they could be independent. There's no requirement on that. We just need their probability to be accumulated to a finite number. So this is the criteria. And part B, we are interested in the other case where B happens with probability 1. But for part B, we need an additional condition. If these events are independent, and the summation of the probabilities diverges, okay. Under these two conditions, we can conclude that with probability 1, infinitely many of these events will occur. So calculating this, the summation of all the probabilities of individual events can give us an indicator on the number of occurrences of these events. Either it is finite or infinite. So for example, let's consider some practical examples. Okay, we can go back to this llama, apply them. Consider independent coin tosses using biased coins. But now we're talking about biased coins, and everything is independent. So we know we are given that for the nth toss, okay, the probability that we observe the head in the nth toss is given by 1 over n. So the first coin is a fair coin. No, so if n equals to 1, the first coin we can only observe head. Okay, with probability 1, we observe head. For the second coin, n equals to 2, it is a fair coin. We observe head with 1 over 2. And as since goes on, the coin becomes unfair. Okay, and this is the probability of head for the nth toss. The question is, what is the probability that infinitely many of these tosses turn head? But if we keep going on, we toss these coins for all the ends, right? We have infinitely many number of tosses. Now, among these tosses, what is the probability that infinitely many of these tosses will turn head? Right? Each toss is an independent trial, and the distribution of head changes over n. Okay, as n goes bigger and okay, let's think about this in the limiting case. If n becomes very, very big, because n is going to infinity, right? We have infinitely many tosses. If n is very, very big, goes to very large number, then at that time, the toss the probability of observing a head is 1 over n, but n is very big. So we have very small probability, very, very small, and this probability is decaying over n. We have a very small probability to observe heads. Right. At the beginning, we may observe head quite often, but later on, the later tosses will have almost zero probability. It's 1 over n, right? It's decaying to zero. We have almost zero probability to observe heads. Now, considering all this set of infinite experiments, what is the probability that this head will be observed for infinitely many times? So for this one, we will have to leverage the Borel-Cantali lemma. So in Borel-Cantali lemma, we just need to calculate the sum of the probability of each individual event. And here we care about the event that we care about is observing a head. So we can define EK as case toss turn head. Okay, we observe a head in the case toss. And according to the statement of problem, we know that the probability of this happens is 1 over k. Because here is 1 over n. The n's toss turn head is 1 over n. So probability of EK is 1 over k. It's a problem statement. So then we calculate the probability, we accumulate all these probabilities from 1 to infinity in the Borel-Cantali lemma. And because it's 1 over k, which is, we know this summation series is almost about the log in k from 1 to infinity. So this goes to infinity. This summation diverges. So we have a divergent summation. Now you go back to the Borel-Cantali lemma. If it's divergent and at the same time, if all these events are independent, then we can conclude something. And in this case, we do have independence. We do have independence among the coins. Right? So we can apply the part B of the BC lemma to conclude that PP equals to 1. So with probability 1, infinitely many of these will occur. So apply the BC lemma, we conclude that this happens with probability 1. So although, and this is not a trivial problem, because intuitively, if you go back to this distribution as the number of tosses gets larger, bigger and bigger, we have very small probability to observe the head. So intuitively, it's hard to say. On one hand, the probability of observing a head is decaying. On the other hand, we are performing infinitely many experiments, independent trials. So will this number will the occurrence of head accumulates to infinity, or is finite? And BC lemma tells us that in this case you do observe infinitely many heads. Okay. So it's not that these conclusions cannot be obtained intuitively without the BC lemma. It's very hard to quantify this intuitively. Yeah.
How can you confidently say that 1 over 20 Yeah.
Okay, so this part, yeah, this summation series, this is a conclusion in math. So this guy goes to infinity. In fact, let's look at more general thing. Let's assume we are summing over k to the power of r. Okay. So if r less than, okay, the summation diverges if r less than equal to 1. It converges if r is bigger than 1. Okay. So 1, r equals to 1 is a boundary between convergence and divergence. I think there are some simple proofs on Wikipedia. So basically you can divide this sequence into some other sequences, and from there you can easily see the divergence of this entire series. But you can also estimate this summation series using integration. So you can roughly say that this summation is roughly equals to integration 1 OK dk k from 1 to infinity, roughly speaking. Right. But then this integration you get is log k, which goes to infinity. The log k diverges. Yeah, and for following this example, if we modify this biased points from 1 over k to 1 over k squared. So for in the case toss, we have 1 over k squared probability to observe the head. If we have such a set of bias, so it is even more biased because as k gets bigger, this probability decays even faster to 0. So the coin is much more biased towards tail, right? So in this case, you calculate the summation series in the ECE lemma, and you find that in this case, 1 over k squared summation is divergent. It is divergent. In fact, it is equal to this number, but anyway, it is divergent. It is convergent. Convergent is a finite number. And then you go back to the BC lemma, you find that, okay, it satisfies the first condition. We don't require anything on EK as long as this is convergent. Then we conclude that the complement happens with 1. So these events, only finitely many of them will occur. Right. With probability 1, we will only observe finitely many heads. But we don't really know how many heads will we observe. It could be 1, could be 100, could be a billion, as long as the number is finite. Could be 1,000 billion, right? As long as it's finite. This is finitely many of this. Right? If you look at here, this B complement equals to 1. Well, B complement means finitely many of this will occur. So, yeah. There's finitely many. Okay, another example. So again, we follow the previous two examples. We specify the probability of observing a head in the nth toss is given by p. It's a parameter. It's a constant parameter. For all the coins, they have the same distribution, but they have the same distribution. So this p does not depend on the coin anymore. But we have more than 50% of chance to observe the head. So these coins are biased towards head. And we define this event EK. EK denotes the event that in the first 2 times K tosses, in the first 2 times K tosses, we observe exactly K heads. Okay. Exactly half of the tosses turn head. Okay. Now the question is, what is the probability that infinitely many of EK infinitely many of EK will occur? So intuitively, do we have an answer for this question? If you look at, forget about BC lemma, just look at the statement. All the coins are biased towards heads, right? It is more likely to observe a head in each toss. It's because P is bigger than 1/2. But EK means that no matter how large the K is, we are looking at exactly half of the tosses turn head. But if this EK happens, then the empirical estimation of P would be K over 2K would be 1/2, right? We have K heads out of 2K tosses. So the empirical estimation of the probability of observing a head is K over 2K. It's just 1/2. But on the other hand, we know the underlying truth is bigger than, strictly bigger than 1/2. So according to the Bernoulli theorem, once we have more and more trials, it is less and less likely that these two will deviate bigger than any number. So this will converge to the underlying probability. Okay. So in that sense, this EK is very unlikely to happen. Very unlikely to happen, because if it happens, it means that this probability is roughly equals to 1/2. But we are given that these coins are biased, are strictly biased coins. So intuitively, we should expect these EK are very rare events, very rare events. But we need to use BC lemma to characterize this, to compute this probability. So to use the BC lemma, we need to calculate probability of EK for each event EK. And EK is very simple by leveraging the combinatorics. Right? With K has out of 2 K tosses, this is exactly the binomial distribution. Well, I need to specify where are the K has located. So I choose K from 2K. Okay, I don't care about their ordering, their positioning. I just need K has, pick K has out of 2K. And then because we observe K has, so we have the probability is P to the power of K. And we have, on the other hand, we have K tails. So this is the probability of each tail, and we have K of them. So this is probability of EK. And to sum them up, okay, to calculate this, we need some approximations because we have factorials, we have exponentials. It's not easy to sum them up because of the factorials. So we need some approximations. Okay. We have approximations. So the K factorial can be approximated by this one. Okay. Well, actually, this approximation is very tight because if you look at both sides, they all depend on square root of K times this factor, right? They all depend on this factor. So the difference is just square root of 2 pi and E. So this approximations. This means that K factorial can be very accurately estimated by such a function. It's a square root of K. This is a polynomial. Well, we have K to the power of K. This is a very big number. So applying this factorial, these approximations to this coefficient, I'm trying to get in a loose upper bound for it. So in that sense, for the numerator, I'm going to use the upper approximation, which is now I'm changing K to be 2K. And in the denominator, in order to be consistent, I need to get a loose upper bound. So for the denominators, I need to use the lower estimation. Okay, and we have PK, this one. Well, if you simplify this becomes very simple. Very simple terms. It's much simpler compared with this. So we only have square root of k over 1 multiplied by a geometric series. And then we can sum them up. So this sum of PEK will be less than equal to sum of these upper bounds. But now this series, the upper bound is clear because, well, this we know that summation of geometric series is convergent. And on the other hand, the coefficient decays to 0. So it is even, this coefficient helps the entire sequence to be convergent. So we can further ignore this k. We know k is bigger than 1. So another upper bound would be simply by ignoring this k. So I just replace all this k by 1, which makes this coefficient bigger, right? And sum over k, well, now we have this geometric series. And for this is p actually. 4p times 1 minus p, this is well, in the condition we are given that p is bigger than 1/2. You can check that if p is bigger than 1/2, then 4p times 1 minus p, this quadratic function is less than 1. It's strictly less than 1. Because this quadratic function, the method, okay, is less than 1. Because, if I can draw this quadratic function, if p goes to 1, it's 0, and something like that. This is 1/2. Okay. When p is 1/2, it achieves the maximum value. Plug it in, it's 1/2, 1/2, 1/2, 4. This is 1. Yeah. So the maximum value is 1. So if p is bigger than 1/2, we are on the right-hand side of this quadratic function. So p is bigger than 1/2, the entire quadratic function is strictly smaller than 1. So therefore, this geometric series, okay, this number, the base number is less than 1. So we know this summation is convergent. So the conclusion is that it is convergent. Okay, even after we kind of upper bounds the previous probabilities by these loose upper bounds. Now these loose upper bounds, even for them, they are convergent. So therefore, the previous summation series has to be convergent. Right, so the conclusion is that this is convergent, and then we call the ECE lemma. We can conclude that infinitely many of them occur with probability 0. And we can conclude that this is probability 0. So basically, you need to figure out a way to determine the convergence or divergence of this series. Yeah.
Just that last part from why you said 4B1 minus B.
Yeah, you just check this one, check this problem. If P is bigger than 0, P is bigger than 1/2, less than 1. This is given by the problem. So 4P times 1 minus P is less than 1. You can sketch this quadratic function, right? You sketch it. This is 1/2, this is 1, this is 0, this is 1, this is P. Right? If you sketch it, you see that between 1/2 and 1, these values are strictly less than 1. Okay, so it's strictly less than 1. So this condition is critical, given in the statement here. This condition is critical. Otherwise, we cannot conclude in this way.
Since we know it's less than 1, then how can we say it's less than 1?
Well, this is less than 1. So this is a geometrically decaying series. So summation has to be convergent.
So we like that less than 10.
Yeah. If this is less than 1, then this series converges. Yeah, if it is equal to 1, then it diverges, right? Everything is 1. Okay, so this concludes the BC lemma. So the BC lemma is very useful for discussing the frequency of the occurrence of a series of events. Right? If you only care about either infinite or finite occurrence, then BC lemma is a very convenient technical tool. But in this lemma, we don't really have many strong conditions. We just need to identify the convergence or divergence of this summation. And if it is divergent, then we need another independence condition on the events. And then this finishes the chapter 1. Well, I think the homework 3 is covered by the combinatorics. Homework 4 is about CDF. I think that is we still need probably another 2 lectures to cover that. So you should have sufficient time for homework 3. So I have 15 minutes. I think I can start talking about random variables. So chapter 2 is about random variables. So the random variables is like we know that in before we have this probability space, right? For a certain experiment, we collect set of outcomes formed to form this omega, okay, omega set. And then we define events as subsets of these outcomes. So we collect some events so that those events can form a sigma algebra. There are some it's compatible with union, intersection, complement, those kind of basic operations. And then we, over this sigma algebra, this algebra of events, we can assign a probability law. So this is the basic structure of a random experiment. But in many cases, we care about statistics. Of outcome. We observe an outcome omega for this experiment, but in many cases we care about some statistics. For example, this omega, if you consider the experiment where each omega, each outcome is the test, the medical test or disease test for 100 people. Okay. So each outcome corresponds to the test results of 100 people. Right? Some of them may be positive, some of them may be negative. Okay. And these outcomes we can describe it as a set, right? We just collect all the possible outcomes and call them the set of all the outcomes. But in practice, we may care about some statistics about this outcome. For example, here I care about the number of positive in this among these 100 people. Okay. So, and these statistics can be defined by a function over omega to real numbers. Right. For example, I can define x omega in this example as the number of positive results. So we are mapping an abstract outcome, right? This outcome can be described by a very general notations, positive, negative, these are notations. We are mapping these outcomes to a number, right? The number of positive results that we observe. So this is a real number, and we call this the statistics. We care about statistics because we want to do some calculations based on that, right, regarding probability later on. So therefore, in many cases, we realize that there's a need to consider a transformation of this probability space under such a mapping. And this mapping maps the outcomes to some real numbers. And those real numbers usually corresponds to some statistics of the outcome. So therefore, inevitably, we have to talk about, so eventually, under this transformation, right, all this omega will become numbers, real numbers. So we have to kind of discuss or define the probability space over real numbers. We need to define a probability space specifically for real numbers. And once we are clear about that, we can start to consider random variables. So the question is, okay, now let's try to define a probability space over real numbers. Well, the set of outcomes is basically the entire real line. All the outcomes are numbers in this case. And so we collect all the real numbers into a set, right? And this is the outcome, the outcome set of this probability space. And following the previous discussion, once we have the outcome, the set of outcome, we need to specify the sigma algebra. And the probability law, right? So the question is, how can we, for these two, how can we define them over the real line? And there are some important observations. Well, in many previous cases, when we talk about sigma algebra, in many cases we can simply consider the power set, which basically contains all the subsets of the outcome space. Just collect all the possible events that forms a sigma algebra. But on real line, turns out we cannot do that. If we want to collect all the subsets of real line, right? Any subset of numbers is a subset of the real line, right? If we want to collect all the subsets of real line, now in this case, we can call this an event, right? Because the subset of the outcome space is called an event. If we want to collect all the proper events, and put them in a set, this set of events, all the set of events cannot so I should say this set of all events. Now this set of all the events on the real line is not a good choice for this sigma algebra. Why? Because once we do that, we can mathematically show that we cannot find a probability law that can be assigned to this sigma algebra. You know, in order to be a valid probability law, the probability law has to satisfy certain conditions, certain axioms. But in this case, if we choose this set to be the sigma algebra over the real line, we can show that there's no proper valid probability laws exist for this sigma algebra. This is because the real line has a very complicated structure. Okay, rational numbers, irrational numbers, and we can have very weird sets, very weird events over the real line. So it's just because of the structure of the real line. So therefore, we cannot do this in such a straightforward way. We have to figure out another way to construct a reasonable sigma field over the real line. And I have 5 minutes left, so I think I can at least introduce the definition of this, the sigma field that we are going to construct. So therefore, we need a special sigma field specifically designed for real line, over the real line. And we call this the Borel sigma field. This is specially designed for over the real line. And this field is generated by open intervals. Now, what is open? What are the open intervals on the real line? You see, it takes the form, right, between A and B. Well, A is less than B, and A and B are real numbers. Okay. So this is an open interval. Well, this interval excludes the A and B, the endpoints. So what do we mean by generate? Right. Generate is like when we do homework 1, we start with a very small set. And then we are trying to generate a sigma algebra over those sets. Right? So that is the generation process to form a proper sigma algebra. And here is the same thing. We start with all the open intervals over the real line. And then in order to form a sigma algebra, we need to make sure the elements in this field satisfy the definitions of sigma algebras. Basically, their intersections, unions, complements are also in this field. So therefore, we simply the generate simply means all complements, countable unions, and countable intersections of open intervals. Right. You start with all the sets of open intervals, and then to generate a sigma algebra, so you start to add these elements to the field. For any open interval, you add this complement to your sigma field. Okay. For any countable union of open intervals, you add this set to your sigma field. For any countable intersections of open intervals, you include them into the sigma field. After this generation process, you will have a complete sigma field generated by open intervals. So we call this the Borel sigma field. And it is specifically designed for real lines because open intervals are fundamental elements of the real line. And this has to be open. Okay? You cannot start with closed. Later we will see. The open is the most general element that we can have. For closed intervals, we can actually create them by intersecting countably infinitely many of open intervals. We will see later. And I think I will stop here. So the next time we will start from the Borel field again, review this definition. And it has many important structures. So once we have this field for the real line, we can talk about real random variables. Okay, so I will take questions in the office hours this afternoon, and we can discuss the homework 3 o'clock. Yeah.